today's lecture we will study the principles of mathematical induction. Now, the principle of mathematical induction provides us a very powerful technique to prove several mathematical results. The basic idea is that suppose we have a statement, or a more precisely a predicate, which depends on a positive integer value n, and we expect it to be true or false for all n greater than or equal to certain fixed positive integer. Then what we can do is to prove this statement for n equal to that fixed integer and assume that the statement is true for some positive integer k which is greater than or equal to that fixed integer, and assuming that it is true for k, prove that the statement is true for k plus 1. Now, let me write formally. Let P n be a statement which for all positive integer n may be either true or false to prove that P n is true for all integers n greater than or equal to 1, it is sufficient to prove 1 P 1 is true, 2 for all k greater than or equal to 1, pk implies pk plus 1. Now, thus we see that if we start from 1 and suppose p1 is true, and suppose for all k greater than or equal to 1, pk implies pk plus 1. This means that if pk is true, then pk plus 1 is true. Now, if we can prove these two facts, then since p1 is true and pk implies pk plus 1, therefore, p2 is also true. Since p2 is true, p3 is also true. So, we will start a chain like this, that p1 is true implying p2 is true, which in turn implies p3 is true, and so on, and this is all for the two facts that we have already proved, that p1 is true and for k greater than or equal to 1, pk implies pk plus 1. Now, what we observe over here is that this number 1 is very specific, and we can relax the situation a little more. So, it may so happen that some statements may not be true for 1, 2, 3 up to a fixed positive integer, but after that the statement may be true for all the other integers greater than that specific integer. In order to bring this slight generalization into our framework, we state this whole principle in a slightly different way. Now, we state that to prove Pn is true for all integers n greater than or equal to n0 where n0 is a fixed positive integer determined previously it suffices to prove that one Pn0 is true, 2 for all k greater than or equal to n0, pk implies pk plus 1. So, this is our slight generalization of the principle of mathematical induction that we stated in the beginning of the lecture. Now, we move on to the required steps in a proof which uses the principle of mathematical induction. A proof by using the principle of mathematical induction has the following steps. One, the first step is called the basis of induction. Basis of induction. In the basis of induction, we have to show that P n 0 is true. If we are unable to show this, then we cannot start induction because it will be meaningless. 2. Induction hypothesis. The induction hypothesis is a hypothesis that Pk, the statement that we get by putting the value of n equal to k, is true. So, we assume that Pk is true. 3. Inductive step. Show that P k plus 1 is true on the basis of the induction hypothesis. If we can successfully complete these 3 steps, then we will have a proof by using mathematical induction. Now, let us look at one example. Now, we are considering the sum of first n positive integers. Let us write Sn equal to 1 plus 2 plus 3 plus and so on up to n. Now, suppose we have a conjecture that Sn is equal to n to n plus 1 divided by 2, and suppose we want to prove this. First of all, let us see that for small values of n this formula works. So, for example, if I put n equal to 1, then S 1 equal to 1, which is equal to 1 into 1 plus 1 divided by 2. N equal to 2, S 2 equal to 1 plus 2, which is equal to 3, and if you look at the formula, it should be 2 plus 1 divided by 2, this is also equal to 3. Therefore, we see that at least for n equal to 1 and 2, Sn equal to n plus n by 2, n plus n plus 1 by 2 works. So, we can form the basis of induction 1, basis of induction for n equal to 1, 1 equal to S 1 equal to 1 into 1 plus 1 divided by 2, which is equal to 1. So, S 1 equal to 1 plus 1 divided by 2 is true, or in other words, S n equal to n into n plus 1 divided by 2 is true for n equal to 1. Now, we move on to the induction hypothesis. In induction hypothesis, we have to choose, we say that suppose for k greater than or equal to 1, S k equal to S k into k plus 1 divided by 2 is true. This is my induction hypothesis. Now, we come to the third point, which is the inductive step. What do we do here? We now start from S k plus 1 and write S k plus 1 as it is defined. This is 1 plus 2 plus 3 plus and so on plus k plus 1. Now, here we observe that we can always sum these first k entries by using the formula that we have already assumed. Therefore, I can write that this is equal to 1 plus 2 plus 3 plus and so on up to k plus 1. This is equal to k into k plus 1 divided by 2 plus k plus 1, and naturally we will sum this expression to get 2 k into k plus 1 plus 2 times k plus 1, which is equal to 2 in the denominator, and on the numerator k plus 1 into k plus 2. The numerator can be written as 2 k plus 1 and then k plus 1 plus 1. Thus, we see that the formula that we wrote over here holds for k plus 1 if we assume that it holds for k. So, this means very strictly speaking S k equal to k into k plus 1 by 2 implies S k plus 1 equal to k plus 1 into k plus 1 plus 1 divided by 2. Thus, this formula Sn equal to n into n plus 1 divided by 2 true is going to be true for all positive integers greater than or equal to 1. This is because we know that it is true for 1 and we know that if it is true for k, it is going to be true for k plus 1. Therefore, since it is true for 1, it is going to be true for 2, since it is true for 2, then it will be going to be true for 3 and so on, and it will cover the set of positive integers. Now, let us look at another example where a problem is solved by using mathematical induction. The problem is as follows: find and prove a formula for the sum of the first n cubes. That is 1 cube plus 2 cube plus 3 cube plus and so on up to n cube. Well, this is of course a difficult problem in the sense that nobody has given me a formula. If a formula is given, I can quickly check whether what I can do by using mathematical induction. For the formula, we need some imagination and some something which cannot be really quantified. But let us check by experiment what happens. So, 1 cube equal to 1 equal to 1 square, 1 cube plus 2 cube equal to 9, which is equal to 3 square, 1 cube plus 2 cube plus 3 cube equal to 36, which is equal to 6 square, 1 cube plus 2 cube plus 3 cube plus 4 cube is equal to 100, which is equal to 10 square. Now, if we go on in this way, we will find that whenever we are taking sum of cubes up to n, it is becoming a perfect square. We can check few more terms. Then somehow we can argue, of course without any possible concrete proof, that probably whatever the sum may be, it is a perfect square, but perfect square of what, that we do not know. Again, if we just sum up to n terms, we will see that 1 equal to 1, 1 plus 2 equal to 3, 1 plus 2 plus 3 equal to 6, 1 plus 2 plus 3 plus 4 equal to 10. Surprisingly, we see that these sum of cubes is it looks like it is as if square of the sum of the usual sum. Now, of course, this is not a proof, but this may lead us to a conjecture like this. Well, this is just a conjecture. Now, what we can see that it is a very neat conjecture, and it is worth checking by using mathematical induction whether this is indeed true. For that, we will start again from basis of induction. Here we see that 1 cube is indeed 1 into 1 plus 1 divided by 2 whole square equal to 1. Thus, we have proved the basis of induction, and now we come to induction hypothesis. Now, induction hypothesis, we assume that Sk equal to k into k plus 1 divided by 2 whole square. Yeah, that is it. For a k greater than or equal to 1. 3. Now, we have inductive step. Again, like before, we consider k plus 1. So, if I have Sk plus 1 and write explicitly the sum, I will get 1 cube plus 2 cube plus 3 cube plus and so on up to k cube plus k plus 1 cube. Again, I observe that the first k terms are essentially Sk, and therefore, since I have assumed Sk equal to k plus 1, k into k plus 1 divided by 2 whole square, I can write this as k square k plus 1 whole square by 2 square plus k plus 1 whole cube. And of course, I can simplify this expression as putting denominator 2 square in the denominator, and on the numerator we have k square k plus 1 whole square plus 2 square k plus 1 whole cube. This gives us 2 square, and here we will have k plus 1 whole square k square plus 4 k plus 4. Now, this gives me 2 square k plus 1 whole square, and this is k plus 2 whole square. Thus, by doing again a small manipulation, we get k plus 1 and k plus 1 within bracket plus 1 whole square. So, the expression k plus 1 whole square into k plus 2 whole square divided by 2 square is equal to k plus 1 into k plus 1 within bracket plus 1 divided by 2, and the whole expression is squared. And we see that this conforms exactly with the formula that I predicted, that is S n equal to n plus 1 n into n plus 1 divided by 2 whole square. Therefore, we can conclude that the conjecture is true. Now, we move on to one more application of mathematical induction, and of course, there are several applications of mathematical induction, and here we will use this mathematical induction to prove something related to logic, specifically De Morgan's laws that we have studied in previous lectures. Let us go to the example. Prove that if n is greater than or equal to 2, then the generalized De Morgan's law that is not of P1 and P2 and so on and Pn biconditional, not of P1 or not of P2 or not of Pn is true. Now, we go on to the solution. Now, here we see that it is somewhat meaningless to start from n equal to 1, it is from n equal to 2, because the De Morgan's law, the one that we have already studied, involves two propositions. So, for n equal to 2, we have not of P1 and P2 biconditional not of P 1 or not of P 2 is true. In fact, we can use our previous knowledge to write that these two statements, not of P 1 intersection P 2 and not of P 1 sorry, not intersection, it is and here, and not of P 1 or not of P 2, they are equivalent, because if the biconditional is always true, that is a tautology, then these two propositions are equivalent. Therefore, we write that P 1 and P 2 not of that is equivalent to not of P 1 or not of P 2. So, this essentially forms the induction hypothesis. I am sorry, this essentially forms the basis of induction. So, I write the statement as this, that I have got a statement P n which is not of P 1, P 2 and P n equivalent to not of P 1 or not of P 2 or not of P n. First step, basis of induction P 2 is true, which is essentially due to De Morgan's law. Now, the second step is induction hypothesis. The induction hypothesis states that P k is true. This means that not of P 1 and so on up to P k is equivalent to not of P 1 and so on up to not of P k. Now, we go to inductive step. So, we start with P k plus 1 which is not of P 1 and up to P k and then and P k plus 1, and now we see that this is equivalent to not of P 1 and P k. We can put a bracket enclosing P 1 up to P k, that is because after all we know that and is associative, and then we put and P k plus 1, and once we have this, we see that we have one proposition P 1 and up to and P k, and then another one is P k plus 1 and not of that, and we can use De Morgan's law for the original De Morgan's law. The reason is that we have proved P 2 is true. Therefore, we will write not of P 1 and so on up to P k or not of P k plus 1. And now, we use the induction hypothesis to write that not of P1 and up to Pk is not of P1 or not of P2 and not of Pk. We can of course enclose this whole expression by bracket, and then it is not of Pk plus 1. And now we know that in this case we can remove the brackets. So, we can write not of P1 or not of P2 or and so on up to not of Pk or not of Pk plus 1. Thus, we see that I have to write equivalences over here. So, thus we see that Pk plus 1 is true. So, Pk implies Pk plus 1 for k greater than or equal to 2. Thus, we see that Pn is true for all n greater than or equal to 2. This completes our proof. Here we see that we have used a slightly different technique, in that we are not only depending on the truth of Pk, but we are depending on truth of P2, which that is what we have proved in the basis of induction step. By this we end today's lecture. Thank you.